Okay, hi everyone. I'd like to introduce Andrew Bolster. He is the head of data science at Black Duck Software. He used to psychoanalyze robots, founder of Farset Labs, former academic, and prolific award winner. And he's going to talk to us today about building beyond buzzwords, productionizing AI in cybersecurity.
Hello folks, yet again it's another AI talk, although hopefully this one's going to be less AI and about more of the stuff that you want to put around AI to make it actually useful. So what do you need to develop, build and operate real AI features in production? But first, who's this for? One, yes, ChatGPT to animated duck, of course, has to be. This is for people who have started their data science journey and are having trouble getting traction or impact on their projects. This is for people on the other side of the house trying to understand and support data science colleagues, and for grumpy old buggers who are tired of people assuming that this stuff is A, new, or B, magical. So we're going to quickly run through a little bit about me. My favorite set of the slides is actually the second bit, which is the history of AI, ML, and LLMs. A little bit of discussion around an abstraction that we use in Black Duck Software for decision support systems. A little bit of a discussion about what does it actually mean to have a system that's production ready? Where are the barriers between proof of concept and production? And how do we go about building systems and not features for production? So, a little bit about me. I'm a perpetual imposter, recovering academic. I live in Python land, ML land. I've spent far too long in the Northern Ireland tech ecosystem not to have some stories to tell. We'll maybe save that for the tipsy bird later. Background in electronics, hacking, lockpicking, and I'm one of the team running the B-Sides Belfast conference. Also sit on the Northern Ireland Open Government Network and sit on the steering committee for InfoSec NI. And as was said at the beginning, I run data science for Black Duck Software. So my development path was a little bit more of careening rather than careering. I started off in software and electronic systems engineering at Queen's with a specialization in digital communication and high-performance computing. This was a really good time to get into GPUs, by the way, whenever they were cheap. And then ended up getting dragged into a PhD because of the economic downturn around about 2000, and got to spend some time doing autonomous warfare analysis for the Ministry of Defense and the French DGA. Asked me about downed Sentinel drones in Iran in 2012. And then once I got out of that, I ended up getting dragged in by a couple of friends, gun gently pointed at my head, to become a quote-unquote data scientist at a bioinformatics startup. What that really meant was, because I had data in the name, it meant that it was everything from real-time cloud-scale analytics down to fixing the Wi-Fi. That we got to spend some time playing with wearables, doing AI analysis of emotional intelligence, VR stuff, loads of fun, and got to throw people down mountains for it. Then I actually got to start doing real work. I got dragged in as a real data scientist in the cybersecurity industry around about 2018, looking at real-time network intrusion detection stuff, real-time analysis of multi-terabytes of network traffic, using bio-inspired algorithms to try and predict hacking and botnets, and mostly making pretty graphs and leaking customer data. Then I got dragged in 2019 as the head of the team lead for the emergent machine learning group in White Hat Security, which my first diktat was, we're calling it data science, not machine learning, and have been stuck there for the past 5 years. I was originally brought in because data science doesn't fit agile engineering, which is something that we're going to talk about in a bit. We've built that system up to automating around about 75 to 80% of the human verification tasks that operate within that business. I reported into the VP of Software Engineering, or VP of SaaS, with quarterly travel to the West Coast and annual to Boston. So if anyone wants to get into cybersecurity, Black Duck's a good company to do it. Anyway, 200 years of work to be an overnight revolution. People think that AI is new. It's not, right? 1769, the mechanical Turk beats Benjamin Franklin at chess. First early indications of humans wanting to use mechanisms to replicate themselves. Then we go even earlier than that, 1736. Who knows anything about Bayes? Bayesian networks, Bayes theory, no, dates back way back when. Then we're going 1833, Babbage's difference engine. Markov in 1913, he was originally analyzing Russian poetry to understand the structure of language. 1922, first use of the word robot. Then we start going in the artificial neuron in 43. We look at the seminal mathematical theory of communication by Shannon in 45. K nearest neighbor. 1951. Perceptron, 57. The first chatbot, Eliza, in 1965. Stochastic gradient descent, 65 again, good year. Fukushima invents convolutional neural networks. Hopfield comes in a couple of years later with recurrent networks. Hinton then turns around and turns those into Boltzmann machines. By the way, they just won the Nobel Prize for Physics. Then we go back propagation in 89, and then we'll do the fold, if this works. Random forests in 1995. Support vector machines, same year, another very good year. 97, long-term, short-term memory, progenitors to today's version of transformer architectures. Then LeCun publishes the MINST database of handwriting samples. Everyone has seen this. Anyone who's read an OCR paper or any kind of vision technology paper in the past, well, 30 years, has seen the MINST data set of those little individual characters. Then we have this little bit of a gap. And actually, I should have highlighted the winters earlier, but we had our first AI winter in the 70s when it was perceptrons were touted to be the solution to everything. Everything was going to be solved by perceptrons and basic neural networks. And because perceptrons couldn't solve the language-to-language translation problem, that kicked off the first AI winter, where basically there was a decade where nothing really got done. Second AI winter was an interesting one because it was actually based on hardware, not software. That was when Lisp machines and the connection machines, the market for those very high-level, massively parallel, neurally defined machines just collapsed. Nobody could justify them. Nobody could afford them. They seemed like a really good idea, but the market didn't match. Then we have this cluster of all of our favorites being established, Amazon, Google, Netflix, Facebook, all just in time for the dot-com bubble. But just before the dot-com bubble, there was another AI winter. This one has been generally considered the buzzword saturation winter. This is where, because everybody called everything AI, then all of a sudden people decided that that wasn't very good marketing. So keep everything on the down low. Round about this period, not a lot happens, but the PyTorch project is like 20 years old, right? Started in Switzerland. Anyway, then we have late 2000s, we come in with a nice big cascade of really cool stuff, and my favorite people, if nobody reads any other of these papers, Goodfellows, Generative Adversarial Networks, really great paper to understand. This is where you're pointing two neural networks at two different targets that are feeding each other. That's when we really start to get into this process of machines training machines, because before this period, an awful lot of this was expert systems driven or people designing algorithms. This period from like 2008 onwards is where AI and ML research really switched over to being a data-driven process rather than a statistical or a code-driven process. Then it just cascades from there. We're looking, this should all be fairly recent memory for everyone. We're looking at the transformer architecture in 2017. Then we have a cascade of all of the GPTs. Good luck keeping up any more than that. I had to update this morning because I forgot about GPT-01. Rough summary, not going to run through all of these. 50s, simple algorithms. 60s, Bayes. 70s, AI winter. 80s, backpropagation, second AI winter. 90s, shift from knowledge-driven approach to data-driven. 2000s, third AI winter, and unsupervised learning. 10s, deep learning starts to be useful. This is when we start doing that data feedback loop. And then the 2020s are ending up being defined as generative AI leads to revolutionary models, blah, blah, blah. I want people to pay attention to this. The commercial potential of AI based on machine learning causes large increases in valuations of companies linked to AI. Valuations, not revenue. Just bear that in mind. So, takeaway here is AI has always been everything that's new, clever, or next until it's mundane. That the developments in AI are clumpy around general advances in hardware or around theory, and that AI winters happen. So, moving on from that one, I want to give the simplest possible explanation I can muster on LLMs. Basically, take a prompt in on the left-hand side, convert that into some kind of embedding that can then be fed through a fancy attention network and basically keep playing the machine forward to see what is generated out the other end, in this case, these green blocks. And based on whatever the attention weights are, you get what the most likely or the least surprising next step in that token sequence. That's it. But it's not that simple. Most likely is doing a hell of a lot of work here, right? You're looking at having a computed weight or a matrix parameter for every single token that's coming in, every single attention head that you might be using in transformer architectures, and then each layer within that head. So this is why, like, GPT-3 has, I think it was 175 billion parameters. Right? Whenever people say parameters, they think that it's some clever thing. It's literally just a floating point number that sits in a matrix. That's it. But it had to be trained iteratively over and over again. But if you want to learn more and do this properly, github.io, Jamar has a fantastic illustrated transformer project, has loads of really cool animations, and Jupyter notebooks, so yeah. Oh, and for anyone wondering, the URL for this presentation is down at the bottom if I move too quickly. The other one, for more pretty pictures, 3 blue, 1 brown, fantastic visual explanations of embedding, deep networks, attention networks, and temperature, which is really useful. And also, if you've got a couple of weeks to spend, the Manim package is really fantastic for building visualizations. Anyway, how do LLMs know things? In my experience, there are only 4 options: training, fine-tuning, prompt engineering, and retrieval augmented generation. Training is basically just whenever you take an existing corpus of data or the entire history of all human knowledge ever and keep showing it to the LLM using masks, where you basically just drop words out of the sentence and then try and get the LLM to predict what's supposed to fill those masks. So this is where you're trying to get it until it works. Your definition of works is your problem. Fine-tuning, same kind of problem, but the idea is that you start off with a basic foundation model that's already been trained, and then you do a little bit more training using your own domain-specific data. Prompt engineering, everyone loves prompt engineering. This is akin to prayer. This is asking the LLM nicely in various ways to do the work better, right? Optimistic at best. And my personal favorite is retrieval augmented generation. This is dead simple. This is give the LLM a search engine. A little bit more detail into how these RAGs actually work. In classical LLM chatbot style, all you're really doing is you're raising a question or an input context. It goes into the magic black box of the LLM, and it spits out the tokens that represent the most likely follow on from that question. So if you phrase a question, it is most likely to give you some kind of answer. RAGs take a slightly different approach by abusing the setup, by taking the original question and then taking the embedding of that question and the keynote or keywords that are used within it to then look up some kind of sexy data store that you will have to build. This data store will consist of various different chunks of individual documents or individual files or pictures or whatever you want, and then by some kind of quantification where you're able to say, hey, which of these chunks might have something to do with this original question. That then leaves you with your top 3, top 5, top whatever chunks. Those chunks then get synthesized into a new context, and then that context plus the original question is what then goes to the magic LLM black box. But what about tool use, prompt flow, assistance, chain of thought, re-ranking, agentic services, hyperchunks, distillation, data fabrics, layhouses, graph of thought? These are all just tools and orchestrations, just like every other type of software that we've been building for 80 plus years. So I'm not going to spend too much time on them. So big takeaways from here. LLMs are big and complex, but simple. It's what is the least surprising next set of tokens based on my context. Common knowledge has been baked into the giant training corpuses that these foundation models are based on, but common sense isn't. And in my opinion, the best use for LLMs is as natural language interfaces to data that you already have if you can constructively RAG it. So, how do we move from the magic of AI into something closer to actual software engineering? We look at abstractions, and an abstraction that we use is decision support systems. So anytime that we're looking at an AI or an ML or an intelligent system, we're only really looking at maybe getting it to do 3 things. You're either automating decisions, generating content, or summarizing existing content. The problem is that if you don't understand the reasons for a decision without context or some kind of confidence, and you just say, here's the answer, you can't actually build trust in that system over time. Similarly, if you can't explain to your target audience what your definition of most likely is, then you're not going to be, end users aren't actually going to be able to make constructive use of that content that's been generated or interrogate it to find out if it's wrong. Similarly, that step of trying to take the semantic meaning from a question to then project it to your RAG store is a very complex and challenging task in there. And you need to be able to input or put in place traceability and actionability so that if somebody turns wrong and says, hey, your chatbot gave me the wrong answer based on this document, the chatbot's not wrong, or it might be wrong, but it might be that the underlying document that it used for generating that discussion was actually wrong, and that the best thing to do, instead of spending another 300,000 GPU hours to fine-tune your model, is just update that Confluence page with the right data. So, I'm not going to go into this, but the long story short is this is an abstraction, or a box that we put around things. We have an input, some kind of state that we're looking to observe and make some kind of decision on, and we have a recommendation that comes out the other side. That recommendation should consist of at least some kind of output context or a classification, including confidences and justifications for why that was the right answer. How does this make it easier to think about how to put these systems in context? It means that you can draw a fairly solid deployment line down the middle and say that this is a deployed module, which is a particular version of a decision support system. If you want to make the new version of that, you have a separate training system that looks after your model tracking, your test train loop, your evals, all of that other good stuff. And then you have this wonderful user loop, which is where you're able to look at a recommendation that comes out of a decision support system, look at how your actual customers interact with that recommendation, and then take that response as a new piece of evidence that you can then add into your training set. So, my personal opinion on this is that if you can identify any kind of interaction point, that interaction point can be an automation point if you've got sufficient feedback. And I like using this as an excuse to say that ML can solve everything. My favorite targets for this are product management, because I think they're actually the ones that are going to get replaced. That's fine. But, so you're looking for an interaction point. This could be a button press, a form submission, a report submission. This could be a Jira task movement. This could be whatever you want. You have some agent that is interacting with a system, and your system has provided that agent with some context, and that agent makes some action in response to that context. This is all fairly simple. In an ideal world, what you should be able to do is then have your draft or your idiot grade ML system able to make suggestions to that agent. Then you're able to watch, hey, does that human actually take that suggestion on board and blindly agree with it? Does it argue with it? Does it disagree with it? Fine. That is all valuable feedback, whether it's positive or negative. It's valuable feedback that you can then continue your training. And then, once you get to the point where your suggestions are being agreed with 90x% of the time, we let product pick what that 90x% is, then you can skip the suggestion step and then just have this now as a newly automated process. Now, you still need to monitor this for data drift and need to monitor that your models are still actually valuable and relevant, but that's going to be very workflow specific. This is the slide that I give to all of our technical leaders, and especially executive leaders, because everyone wants AI applications, but they are not always willing to invest in the stuff that you need beforehand. You need consistent data. That's the one that everyone talks about, so I'm not going to belabor that one too much. But the bit that people don't talk about quite as much is persistent feedback. Like, if you don't have a workflow that exists within your product space that gives you that feedback, you're not going to be able to do any of this. Similarly, if you don't have risk acceptance where you can accept a 1, 2, or 5% likelihood of having the wrong answer, then you're not going to be able to build up that feedback loop to make sure that this is actually working properly. Takeaways on this one: intelligent systems should support decision-making, not necessarily replace it. Identifying interaction points can make it a lot easier for identifying opportunities to improve systems, and any intelligent system is only as good as the feedback that you collect. Now, what does it mean to be production ready? Sales, support, and solicitors. So most AI and data scientists live in the code land. Maybe if they've got a background in SWE, they might go into plan and build. But the code works, you've got your Jupyter notebook, it's fine, it's all ready to rock and roll, right? The problem then comes whenever you start going, how are you doing version control on this? How are you tracking changes? How are you packaging this? And how is this being distributed to different systems that you want to run it on? Do you have any systemic dependencies? How do you keep those dependencies up to date? How do you need a separate compilation and build step? Can you do transpilation? Are you looking at multiple machine targets? Do you have any code quality standards or any kind of checks in that regard? Do you have unit tests? The number of data scientists who write unit tests is basically like 0. What about integration tests? What about whenever you start plugging this into other systems? What does that mean to those other systems? Do they need to test differently based on whether the input's coming from a machine or coming from an agent? What about updating documentation and operational runbooks? If your decision support system starts going haywire, how do they step out of that and protect the running production system? Versioning and change logs. How do you communicate that as part of the release process? Do you communicate every single time that you run a model update? Do you just do major architectural changes? What about setting up dev and staging environments? How do you have that balanced interaction between production level quality and data science flexibility? Do you need to notify customers of changes of behavior? This is one thing that data scientists really don't think about, is how do we need to communicate this forward and outward? Do you need to get sales and marketing involved? Do we need to send out a grand bulletin to know how much we're doing? Do you need to have a new kind of customer support? Is there anyone in your L2 or L1, L2, L3 support stream that can actually discuss anything about your decision support system? What about on-call support? Like, if this all goes to shit, do they call you? What about integrations and third-party partnerships? What happens whenever you've got metrics and observability and alerts? Do you have any of that? What happens whenever you have customer feedback, whenever the customer says, oh, it's going really well, but I keep dismissing this suggestion? Do you have that follow-through? And then last but not least, do you have any idea how much this is going to cost? A lot. But here's the scary bit. There's like 6 different teams in there, all right? That's software engineering, quality assurance, technical copywriting, cloud operations, customer success, sales and product management. I didn't even leave them on, but there is an executive oversight here, right? I just did the code. Why do we do all of this? What has software engineering been doing for 30 years that's what we end up with? Well, here's the problem. Compute is expensive. Code is more expensive. Broken code is most expensive. Testing is cheap. Earlier you can test, earlier you can integrate, the better. Stability. Customers don't like systems that they cannot trust. And customers pay lawyers to sue products that break that trust. And repeatability. It's been said that novelty is the engine of innovation, but I call bullshit on this. Patterns are the engine of success, having a shape and a form that you can replicate over and over again to take your novelty forward in a structured way. So what are our takeaways from this bit? The distance between works on my machine and an actual product is a hell of a lot further away than you think it is. What is a cool experiment to you is a potential reputational and legal risk to the enterprise. R&D is easy, integration is hard. Make friends and collaborate early. So, how do we go far together? Over the past 2-3 years, we've all seen this where AI appears to be magical until it's not. There are lots of quality or skill issues where especially LLMs give inconsistent responses, and you know, it's not a consistent customer journey. But there's also difficulty in establishing intellectual property and business unique selling points and growing value. If you're just saying to Sam Altman, dear ChatGPT or dear O1, you are a customer success manager, do my job for me, thanks. That's not the business growing any additional capability or intellectual property. That's you just giving money to Sam, or I suppose giving money to Microsoft via Sam. Anyway. People love building shit in caves. Proof of concepts are easy, works on my machine, but the problem is that whenever you're looking at building hundreds or thousands of these a day, and you want to sell them to customers that have legal teams, proof of concept isn't going to be enough. So, we talked about the DevOps loop. What does it actually take to run an intelligent service? Oh, you've got your LLM, you've got your API call out to ChatGPT, fine. Oh, you've got network access control lists, that makes it secure, great. However, do you have experience in how to author, manage, and change control prompt flows? Or what guardrails do you have that monitor for negative content coming into or out of the LLM? What's your conversational memory? Do you have a policy for managing previous interactions that a system has had with an individual user? Is that covered under your terms of service? Are your existing knowledge bases ready to be queried by a new type of intelligent system? Do you have APIs that can actually just be plugged into, I know that GitHub Copilot just released an update to their extensions, where you basically, if you want a new agent, you just give it a well-formed API, and it'll build a cool service for you. The problem is, if you don't have those APIs, what are you going to do? And then there's a load of other shit in there as well. The big thing is, checkbox exercises and gimmicks will reduce overall trust in the business. So, how do we actually build out those capabilities? Well, you need people. So that means investment in R&D, investment in relationships with product and software engineering teams. It means data management. Do you have sensible data stores? Is data well governed? Is access mitigated in a sensible way? Do you have a classification system that empowers people to safely use data instead of, oh shit, we pushed this to production and we realized that we just trained this on a whole pile of ITAR related data? That happened, by the way. Generic model creation. Do you have any maturity in basic ML ops of being able to explore data? Do you have experimental compute that's well budgeted that you can then turn around and say, hey, I made this little test thing and it's not going to blow up in your face? Do we have any kind of experience in model deployment, release, and monitoring? That's not even starting into the LLM shit. Like, do we have a process for being able to quantify the relative behavior whenever a new version of GPT comes out? Or whenever you want to switch over to Claude, or whether you want to switch over to Anthropic, or you want to switch over to your in-house Llama one that some guy built on a couple of leftover GPUs. And then the boring one. How do you get it into the rest of your product suite? Do you have a way of engaging with your existing product teams to inject these novel capabilities without screwing up both of your days? This is the kind of maturity model that people need to start looking at, and this is intentionally the eye test version. And I know this is being recorded, so I will leave it to the audience to work out what these color grades mean. But this is the kind of stuff that you need to do if you think that you're going to be a leading AI ML participant. So what's the advice? Stick to the interaction points. Context action data is your absolute king. Start making predictions early and measure as much as you can. Once you get to the point where you're better than a coin flip, race as quickly as you can to make friends with operations and compliance to make sure that you haven't screwed up so far, and then get into production as quickly as you can, making suggestions to your actual users. Measure the acceptance, and then keep going. So, final slide, I promise. What do you want to take away from this? Buzzwords can kill the entire market. AI has a history of being a term for any technology that we don't use regularly yet. Interaction points. There's the quote from, I can't remember, I want to say Aristotle, but sure. Give me a fulcrum and I'll automate the world. Give me an interaction point and I'll automate whatever workflow you want. Hallucinations. LLMs don't lie. They just blabber without any regard for the truth. And that's fine. Production. The distance between works on my machine and an actual product is a hell of a lot further away than you actually think. And then systems. To cross that distance from proof of concept to production, you're not going to be able to do it yourself. You need to bring a clan along with you. And that's it. Thank you very much, folks.